So I'd like to prove an awesome theorem about planar graphs called Euler's formula. This is one of my favorite facts about graphs. And it basically says that for any planar connected graph, the following is true. The number of vertices, so that means the number of vertices, minus the number of edges, plus the number of regions in the graph, always equals 2. Okay, so for example, we look at this triangle. The number of vertices is 3. The number of edges is 3. And the number of regions, we have this inner region and the outer region. Well, it does indeed equal 2. Here's an even simpler graph. So the number of vertices is 4. The number of edges is 3. The number of regions is just 1. It's the outer region. Again, this equals 2. So it is the case that for any planar connected graph, the number of vertices minus the number of edges plus the number of regions equals 2. Okay, and we're going to prove this in cases. So let's do case 1. Case 1 is that the graph, the planar graph, G, is a tree. What does it mean to be a tree? It means that there are no cycles, right? So the graph looks something like this. But in any event, since the graph G is a tree, it means that there are no cycles in the graph. Since there are no cycles, it implies that there's only one region, the outer region. Think about it. Since it's a tree, there are no cycles. So there can't be any sort of enclosed regions in the graph. So the only region must be the outer region. So if it's a tree, there's only one region. Now we've proved that in a previous video that for any tree with n vertices, there are n minus 1 edges. Great, so now we know that for any tree, there are always, for any tree, let's say it has n vertices, that means there are always n minus 1 edges, and there's only one region, the outer region. And you'll notice that n minus n plus 1, this equals 2. So for any tree, Euler's formula is definitely true. Again, that's because since the graph has no cycles, there's only one outer region. And since it's a tree with n vertices, it means that there are n minus 1 edges. So if there are n vertices, we know there are n minus 1 edges. There's one region. We add them up. We get 2. Now we're going to prove the rest of Euler's formula. So case 1 was that the graph was a tree. Remember, this is what we're trying to prove. Let's do case 2. So this is the graph is not a tree. So the graph has a cycle. And now I'm going to prove by induction on the number of edges. So I'm going to prove by induction on the number of edges that any planar graph with a cycle with a cycle, I guess I should say, obeys Euler's formula. And again, these are any connected planar graph where the cycle obeys Euler's formula. Even in case 1, we used the fact that the tree was connected because we said there was only one outer region. So if it wasn't connected, there would be more than one outer region. Okay, so what's P of n? It's any graph with a cycle, it's connected, and planar, obeys Euler's formula. I guess I should say any graph with n edges. I mean, we're using n here, P of n. Any graph with n edges that has a cycle, it's connected and planar, obeys Euler's formula. Okay, so let's remember this is P of n. So let's assume P of n is true and prove P of n plus 1. So let G be a graph with n plus 1 edges with a cycle. Okay, so since G is a graph with a cycle, we don't know how many edges are in this cycle, but somewhere in the graph there is a cycle. Who knows what the rest of the graph looks like, but there's a cycle sitting somewhere in the graph. So what I'm going to do is choose an edge on the cycle. Let's say it's this one. Okay, I'm going to call this edge E. So remove E from the graph. Okay, and we'll obtain, so now we've obtained a new graph. Let's call it G prime. So, by the inductive hypothesis, G prime obeys Euler's formula. Okay, now how many vertices does G prime have? Well, G prime has the same number of vertices as G. So if G had V vertices, then G prime has V vertices. Right? We didn't remove a vertex, we removed an edge. How many edges does G prime have? Well, if G had E edges, then G prime has E minus 1 edges. Right? We removed one edge. And how many regions does G prime have? Well, if G had R regions, when we take out this edge, we're destroying this region in here. So ripping out this edge destroys this region because we've removed one of its bounding edges. So if G had R regions, G prime has R minus 1 regions. Okay, so G prime obeys Euler's formula. What does that mean? Well, the number of vertices of G prime, which is V, minus the number of edges of G prime, which is E minus 1, plus the number of regions of G prime, which is R minus 1, has to equal 2. Now right here you might say, well, hey, can you use the inductive hypothesis on G prime? What if G prime doesn't have a cycle? If G prime doesn't have a cycle, then it's a tree. And we know that Euler's formula holds for trees, so Euler's formula will also hold for G prime if it's a tree. If it's not a tree, then we're using the inductive hypothesis here, and we're assuming that Euler's formula holds for G prime. So the number of vertices of G prime minus its edges plus its regions has to equal 2. I'm just going to simplify this expression. So this is V minus E plus 1 plus R minus 1 equals 2. And then I have 1 here and minus 1 there. So I'm left with V minus E plus R equals 2. But notice this is exactly what we wanted to prove. We took G and we proved it has n plus 1 vertices. We proved that its vertices, G has n plus 1 edges. We proved that G's vertices minus its edges plus its regions equals 2. It's kind of a slick trick. We ripped out one edge, we applied Euler's formula from G prime, and we did a totally simple arithmetic simplification to get Euler's formula back for G. So I suggest that you rewind the video and kind of look over this proof. It's totally valid, and it's totally simple. I'm a big fan of this proof. Oh, I guess I forgot to do the base case for this particular proof by induction. We should do that. The base case is P of 3. So you need to look at a graph that has 3 edges and has a cycle. The only graph that satisfies that is this triangle, and it's easy to see that Euler's formula holds for a triangle. So that proves the base case.